Okay, so in this video, I'm going to talk about uh, mixing in real reactors and residence time distributions. So, as we've been thinking about reactor design in this class, one of the assumptions that we have made is that all reactors are perfectly mixed. But real reactors aren't always perfectly mixed. And the way we describe that is by saying that different molecules within the reactors have different residence times. So whereas in an ideal reactor, such as an ideal PFR, for example, or an ideal batch reactor, all of the molecules spend exactly the same amount of time in the reactor, and that is the residence time. That is not the case for the CSTR, and I'll show that in just a minute. In a real reactor, you're going to have a distribution of residence times. And why that's important is because it influences the chemical reactions, taking place inside the reactor, and it influences the performance of the reactor. So, for example, the product distribution in a reactor with non-ideal mixing will be different than in a reactor with ideal mixing. And we're going to show that over the next couple of lectures. Okay, so going to the notes, so far in this class we have studied ideal reactors where we have assumed perfect mixing. For example, in the batch reactor and the CSTR, so in our tank reactors, we have assumed that the contents of the entire tank have the same concentration, the same temperature, the same amount of catalyst, etc., so the same properties. In other words, that there are no gradients over the entire volume. In our tubular reactors, the PFR and PBR, we have assumed perfect mixing in the radial dimension, and no mixing in the axial dimension. And what we mean by that is if we have a tubular reactor and we have some volume slice, and this is a hypothetical slice. It doesn't physically exist. It's something that we think about to understand reactor performance. What we're saying is that within this entire volume, everything is well mixed, so there's no gradients inside this volume. So everything in there is the same concentration, the same temperature, but if we were to go to the very next volume slice, now all of a sudden there's a difference. So the temperature, concentration are varying down the length of the reactor, but at any position along the length, the properties are uniform. So at any position along the length, properties are uniform and properties vary continuously down the length. Okay. Maybe I should redo that. There. Okay, so real reactors are not as perfectly mixed. So for example, this is an example of a a packed bed reactor, the circles here are catalyst pellets. And as you can see, the catalyst pellets are not perfectly packed. So there's some places where there's large voids and there's some places where there's very small voids. But if you think about flow trying to go down that reactor, it's going to take various paths. So for example, it could take a path such as the one labeled path 1, which has low resistance, molecules through this path faster. Or it could take a path with more resistance. So for example, this path labeled path 2, this has higher resistance, and the molecules move through more slowly. And the reason for that is there's less void space, so the molecules are coming in contact with more catalyst particles. So you can imagine if in path 2 the molecules are coming into contact with more catalyst particles, then more of the reactants there are getting converted into products than in path 1. So path 1, the molecules are seeing fewer catalyst pellets, so fewer of the molecules are getting converted to products. So you're going to get different conversions here based on the different residence times in these two pathways. In a tank reactor, so I'm going to show in a second that in a CSTR, even if you have perfect mixing, you have a residence time distribution, even in an ideal CSTR. But in a non-ideal tank reactor such as this one, you might have a dead zone. So the stir, for example, is unable to mix this material here. So stir is ineffective at mixing this region. And you might have seen examples of such things in your real life when you're trying to mix something and part of that volume doesn't get quite mixed. That can happen in a reactor as well. That's called a dead zone. In the dead zone, the molecules do not mix with the rest of the volume. And hence they never leave. So those molecules in that dead zone, they're trapped. So looking at all of these different examples, what we see here is that different molecules spend different amounts of time in the reactor. In contrast, in ideal PFRs and PBRs and batch reactors, all of the molecules spend the same amount of time in the reactor. So if you think about a batch reactor, so we have our batch reactor, and then what we do is we want to fill the reactor. So we fill the reactor. After we fill the reactor, then we let the reaction run. So turn on the stir, heat up to catalyst or to reaction temperature, etc., and let the reaction run. So now we're reacting. As we react, what's happening is that if we took concentration versus time, our reactant concentrations are decreasing and our product concentrations are increasing. Once we achieve some desired conversion, what we do is empty the reactor. So we drain the reactor. So basically what happened there is every single one of those molecules spent the exact same amount of time inside that reactor, basically from the time it was filled to reacted to draining. Similarly, in the PBR and PFR, since based on the assumptions that we've made where there's no mixing in the axial dimension, what that means is that molecules are kind of staying constrained within these volume slices. So your molecules might enter in this volume slice, and let's see if I can, no, I'm not going to be able to, okay. And what's going to happen is as this volume slice flows down the reactor, and then it's going to exit. So then, and when I did that, I of course kept all of that here. I didn't mean to take them out of the reactor with me. But basically what happened was those molecules all spent the same amount of time in the reactor. So if we draw that, excuse my poor animating skills, we have this volume slice, and this is going to flow until it eventually exits the reactor. But every single molecule that enters some hypothetical volume slice and travels through the reactor in that volume slice, and hence spends the exact same amount of time in the reactor. In a CSTR, it's different. So my CSTR looks like this. I have a stir. I have some fluid in there. I have stuff coming in and stuff coming out. So I have molecules that come in. These are the molecules that originally come in, and basically what happens is some of these molecules, since they come in, and it's as soon as they enter the reactor under the CSTR assumption, the volume becomes entirely well mixed. What this means is that some of the molecules leave right away. So some of them are going to leave right away. Others are going to stay in here for quite a long time. So they're going to move around and be mixed around, and who knows if they ever come out. So some are going to stay in there for quite some time, and that's just the nature of the CSTR. It's a very big volume. It's assumed to be well mixed. You basically dump in contents, and the minute those contents enter, they are well mixed. So they're part of this entire volume. They have no memory of when they entered the reactor. So because of that, we have a distribution of residence times within the reactor. However, because this is an ideal CSTR, there is an average residence time, and the average residence time is based on the design of the reactor. So it's going to be equal to the volume, or the volume divided by the volumetric flow rate. But what's happening in here is that some molecules exit right away. Some circulate and remain in the reactor a long time. Okay, so this is kind of an illustration of a residence time distribution. So the CSTR has that. So some molecules exit right away, so basically are in the reactor very little time, and some stay in there a long time. So there's a distribution of times at which the molecules stay in the reactor. What this looks like is we can plot the probability molecule resides in the reactor for time t versus t for an ideal CSTR that looks something like this. It's an exponential decay function, and so it goes on for infinity. I just haven't drawn it like that. For a PBR or a PFR, this is the same probability. I'm just not going to write it all out. Versus time, I basically have a very poorly drawn direct delta function. But basically, all of those, every molecule spends the same amount of time in the reactor. So I basically just have one place along the time axis, and all molecules fall under that. Those are for ideal reactors. Of course, residence time distributions also occur in non-ideal PFRs and PBRs, and we saw that above in our catalyst example. Conversions in real reactors are usually lower than in ideal reactors. This is not always the case. Sometimes the conversion is higher. So it's one of the many things about reactor design that there is no generality. And the reason that the conversion is typically lower is due to ineffective contacting between molecules. So if there's ineffective mixing, what that tells us is that there's going to be ineffective reaction.